Good morning, class. We are shifting into Chapter 5 today. And Chapter 5 is all about a different growth pattern and ways of writing down growth patterns called sequences. So there are two types of sequences we'll be dealing with this chapter. One of them is very familiar to us. It's called an arithmetic sequence. And in that, it's pretty much like it's a linear relationship, except our domain's going to be restricted. The one that we're going to start looking at today is a geometric sequence, but we'll get more into that vocabulary and what that means later on. So let's start with Chapter 5. In fact, Section 1.1. The title is How Does the Pattern Grow? Representing Growth. So far this year, and actually last year, and even some before that, right? We've been dealing a lot with the family of linear functions, and we're getting pretty good at using multiple representations to show linear functions. So for example, I could create a table of values, and in a table of values I could have my domain values, right? These are the x values along the x-axis. And I'm starting arbitrarily at 0 here. I could have negative numbers as well. But I do like knowing what the 0 value is, because across from that is where I begin. So I could write down my values here: 7, 9, 11, 13, 15, and 17. And if you look at this, what's happening is every single time I move forward one in the pattern, I'm increasing by adding 2. 7, 8, 9, 9, 10, 11, 11, 12, 13. 13, 14, 15, 15, 16, 17. So that means that my slope is 2. Literally, my rise, as I increase by 2 units, I could do, for example, 15 minus 13 is 2, and my run was 1. I increased by 1. So 2 divided by 1 is a slope of 2, and my y-intercept is 7. So another representation for that is this equation, y equals 2x plus 7. And we can also do the representation of looking this on a graph, right? So if my domain is restricted to just these integer values, including 0, actually, we'll just call them integers. The integers would also include the negatives as well. But if I'm restricted to just the whole numbers, I wouldn't connect these dots. I would just leave these as they are. But I go from when x is 0, y is 7, etc. Today we're going to start learning about a new family of functions called exponential functions, and we're going to talk about the type of growth that it models. So you either have or you will soon this year. I think most students in the 9th grade read Of Mice and Men, and in the book of Mice and Men, written by John Steinbeck, two good friends named Lenny and George dream of raising rabbits and living off the land. What if their dream came true? Suppose Lenny and George started with just 2 rabbits. Here they are, 2 rabbits. And during the first month, those 2 rabbits have 2 babies. Well, first of all, we have to put them in an idyllic, a beautiful scene painted by Bob Ross. There it is. You can see the happy trees, and you can see the happy rabbits. So what we're saying is, suppose during the first month, those 2 rabbits have 2 babies. So let's come back here. So there's a couple things that are important, but we're just going to say, suppose these 2 rabbits have 2 babies. So 2 gave us 2. So at month 0, we had 2, and at the end of the first month, we have 4. Also suppose that every month thereafter, each pair of rabbits has 2 babies. So here's a pair, and here's a pair. They're not going anywhere. They had this pair already, but each month, every pair that I see is going to create a new pair of bunnies. So this pair creates a pair, this pair creates a pair. Then when I go to my next month, right, you can see each pair, this pair had a 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 pair. So this is the growth that we're describing here. So with your team, determine how many rabbits Lenny and George would have after 12 months, which is 1 full year. Represent this situation with a written description of the pattern of growth, a diagram, and a table. So you don't have to draw pictures of bunnies, but it would definitely be nice to have, you know, maybe 2 dots that represents a pair of rabbits, and then show that after a month that pair has a pair. So some kind of a diagram like that. So I'm asking you to represent this situation with a written description of the pattern of growth, a diagram, and a table. State the assumptions you made when you modeled the number of rabbits raised. So we would have a conversation about that in class, but there's some things that we clearly have to assume, right? That they're not injured, that they're healthy, that we have a male-female pair in order for this to continue. Compare any patterns you find to other patterns you've already previously investigated. So I would like for you to, at this point, you don't need me to talk about this much. At this point, I'd like for you to look in your ebook, and we're doing questions 5, and I do want you to do 5-1, so it's question 1 in chapter 5 and question 2 in chapter 5. And I want you to do that further guidance section, which is question 2. So make sure you answer both of those. My suggestion is, in this case, that you open up an e-doc or a Google Doc, and that you submit that for your written work or typed work today. So go ahead and take some time to do questions 1 and 2, and then when you're ready, unpause this video and we'll go on and discuss question 3. Okay, so let's move on to question 3. But so for question, you've done 5-1 or question 1 and question 2. So if we were to continue this pattern, of course, the number of rabbits does grow quite rapidly, and keeping track of that is probably better done with a table. Notice that if we were to fill in the values in this table, it becomes much more advantageous. So after 1 month, right, we have 4 rabbits. After 2 months, right, each pair is going to have a pair. So we're literally going to go from 4 to 8 rabbits. After 3 months, we have 16. After 4 months, we have 32 rabbits. After 5 months, we're at 64, etc.